Today we're going to talk about rational functions. A rational function is a function that has the form of a polynomial numerator and a polynomial denominator. And we're going to be graphing these. So the things that are important to us will be the domain, which would be all real numbers except the things that zero out the denominator. Vertical asymptotes, which are expressed as x equals some number a, where a is a zero of the simplified function, and we'll talk about what that means. A removable discontinuity, which is a point, x, or a comma something, which creates a hole in the graph, and it gets created by a factor that could be canceled out of the numerator and denominator. And so we find a, and then we plug a into the simplified function to find the y coordinate. These three things go together. Every exception in your domain will either be a vertical asymptote or a removable discontinuity. Never both, but every one of those except values must be accounted for as a vertical asymptote or a removable discontinuity. Then we have horizontal asymptotes as a horizontal line, so y equals some value b. It determines the end behavior of a rational function. So, and the conditions for that are these. If the degree of the numerator is higher than the degree of the denominator, then there is no horizontal asymptote. If the degree of the numerator is lower than the degree of the denominator, then the horizontal asymptote is at the x-axis, or y equals 0. And if the degrees are the same, then the horizontal asymptote is the fraction created by the leading coefficient of the numerator over the leading coefficient of the denominator. And all that will make much more sense once we take a look at a couple of these. Okay, so f of x equals 1 over x. So my domain would be all real numbers, except x couldn't equal 0, right? X is not 0, because that would zero out the denominator. There's nothing I can cancel, so I do not have a removable discontinuity. No. So that means 0 is my vertical asymptote. Okay, those three things go together. My horizontal asymptote is determined by the degree of the numerator, which is 0, right? X, there's no x's in it, so x to the 0 power, over 1. So the denominator has a higher power, so it is at y equals 0. Okay, so now we're going to graph this. Straight lines would help. Our asymptotes, I would suggest doing them in highlighter. So horizontal asymptote at y equals 0. Vertical asymptote at x equals 0. And then we need to plot some points. For this one, I don't think we need our calculator to create a table of values. If I plug in 1, 1 over 1 is 1. If I plug in 2, 1 over 2 is 1/2. If I plug in 3, 1 over 3 is 1/3. If I plug in 4, 1/4. If I plug in 1/2, 1 over 1/2 would be like 1 times 2 over 1, so that would be 2. And my graph, you can see, is approaching the vertical asymptote this way and the horizontal asymptote this way. Right? The notion of asymptote will sort of come toward it. On the negative side, 1 over negative 1 is negative 1. 1 over negative 2 is negative 1/2. 1 over negative 3 is negative 1/3. 1 over negative 1/2 would be 2. And again, as soon as I get enough points to see how it is approaching the asymptotes, I draw. Okay, so for this one, this is the basic, when we talk basic graphs, this is the basic rational function. So let's make something else go on. So here we go. My domain would be all real numbers, except x cannot be -4, right, because that would zero out the denominator. Both of these are completely factored and nothing cancels, so I have no removable discontinuity, which means that my x cannot be negative 4 is now a vertical asymptote at x equals 4. Those things go together. My horizontal asymptote, well, the degree of the numerator is 1, and the degree of the denominator is 1, and so they are the same. So the leading coefficient here is 2, and the leading coefficient here is 1. So y equals 2 over 1, which is 2. Okay, so let's draw this. Okay, my vertical asymptote is at 4. I'm going to use these to count by ones now. So that's at 4. My horizontal asymptote is at y equals 2. So I've created the same sort of one vertical and a horizontal asymptote. So I'm probably going to get a graph that looks similar to the last one, but it's going to be in a different place. You can either plug in points, or I'm guessing you may want to use your calculator. Keep in mind the calculator needs numerator in parentheses and denominator in parentheses. So my numerator, 2x, divided by my denominator, x plus 4. Okay. Oh, did I copy that wrong? Oh, negative 4. Whoops. I put my asymptote in the wrong place. Let's move that asymptote. Negative. Okay. Phew, good thing I caught that. All right, so now I'm going to look at the table of values. My table is showing me negative 10. You can use up and down arrows to grab some values. Okay, so I'm seeing the asymptote at negative 4, and I want to pick up a few values on either side of that. So negative 6 is 6, and negative 5 is 10. Negative 6 is 2, 4, 6. Take a minute. And negative 5 is 10, 2, 4, 6, 8, 10. And I can remember negative 7 was like 4.6 repeating. So that would be about 2, 4, and 6 repeating about here. So I can see that this one over here is going like this. And then on the other side of my asymptote, my table is showing negative 3 is at negative 6. Negative 2 is at negative 2. Negative 3 is at negative 6. And negative 2 is at negative 3. And negative 1 was at negative 0.6 repeating. Negative 1 was at negative 0.6 repeating. If you want to grab more, that's very conscientious. The 0 is at 0, and 1 is at 0.4. 0 is at 0, and 1 is at 0.4. But at this point, I can see that this graph is going like this. Once I've done my graph, I can actually maybe take a look at the graph, and it confirms what I have drawn. But I would not suggest looking at the graph before you plot some points. If you use your calculator to get points, I would like you to include the table of values with your work. Okay, this one a little more involved. So we have the denominator factors into x plus 2, x plus 1. So we are going to get some canceling here. But before we do that, domain, all real numbers, except x is not -2 or -1. We will get some canceling. So we are going to get a removable discontinuity. Let me cancel those in red. So my simplified form is 1 over x plus 1. Okay. So then my removable discontinuity, well, the one that I canceled was the one that went with -2. And so I plug that into my simplified version, and I get 1 over -2 plus 1. So 1 over -1. So -1. So what's going to happen is there's going to be a little hole in the graph at -2, -1. The one that didn't cancel becomes my vertical asymptote. So x equals -1. Notice those things went together. My horizontal asymptote, I would work from my simplified version. So the degree of the numerator is smaller, so that's y equals 0 for my horizontal asymptote. Okay, so let's draw this. My vertical asymptote is at x equals -1, and my horizontal asymptote is at y equals 0. I have a hole in the graph at -2, -1. So I draw that like a little hole in the graph. And now I need to go and grab some values. I'm going to punch in the simplified version because it's easier. So 1 over x plus 1. Just so that I'm still in the habit of putting my numerator in parentheses and my denominator in parentheses, I'm going to do that. Sometimes you don't have to, but let's graph this. Oh, that's not what I meant to do. No peeking. Wait, don't look. I want to look at the table. Okay, so I want to be on either side of -1. So -5 is -0.25, and -4 is -0.2 repeating. Okay, so this is 245.25, -1/3, -3 is at -1/2. -3 is at -1/2. And then there's my hole, which is showing up in my table. It's saying -2, -1. Then there's my asymptote. Then 0, 1, and 1, 1/2. So 0, 1, and 1, 1/2. Okay, so I'm still getting this look. And maybe after you graph a couple of them, you get a strong sense that when you have one vertical and one horizontal asymptote, you're just trying to get enough points to see that the shape is here. Okay, and there's our hole. There's the change. We have a removable discontinuity. Okay. This denominator will factor into x plus 4, x minus 2, and we will have no canceling. So our domain, all real numbers, except x is not -4 or +2. Because there's no canceling, and we have no removable discontinuities. So both of those will be vertical asymptotes. X equals -4 and x equals 2. My horizontal asymptote, the degree of the numerator is again smaller than the degree of the denominator, so y equals 0. -4 and +2. And horizontal asymptote. Okay, so we have now 3 sections. This is a different look. You know, my asymptotes are making the letter H. So there's going to be a piece over here that looks probably either like this or like this. There's also going to be a piece over here that either looks like this or like this. But in the middle, just about anything can happen, but something is going to happen. Okay, so we have y equals, figure that out, 3 divided by x squared plus 2x minus 8. Okay, I want to get my table. Again, oh, no peeking. Okay, so I need to get a couple of values before my first vertical asymptote. So -7 is about 0.11, -6 is about 0.19, -5 is about 0.42. So really, really close to the origin. 0.11, 0.12. That's all I've got. But really, if I have done enough of these, I know that the shape on this side, I know it's above. So it's obviously approaching here. And it's on the upswing here. Okay, between the two, I've got, between my two asymptotes, kind of a very symmetric look. So negative, but they're all negative. -0.6, -0.38, -0.33, -0.38, -0.6. Okay, so -0.6, a little higher, a little higher. 0 is coming back down. So I get kind of a look like this in the middle. And then beyond the asymptote, the second asymptote, I'm at positive 0.42, positive 0.43, positive 0.19, positive 0.42, like this. So the look of this one is again on the top side. Again, if you're using your calculator, please show me the table of values so I know what you were trying to plot. At this point, we should look at the graph. Notice that the calculator sort of stops drawing. Yeah, it stops drawing. So be careful. Your calculator sometimes has pixel issues and cannot show you an as accurate a graph. Let's see how we're doing on time. I have to stop here. So good luck to you.